Welcome. In the last session, we looked at two examples of finding limits of rational functions, actually one polynomial, one rational function. That process works in general, and so by following the same steps, we can verify the following facts. First of all, for polynomial functions, limit equals value. So if f of x is a polynomial and c is any number, then the limit as x approaches c of f of x exists and is equals f of c. What if you have a rational function that's not a polynomial? Now first you simplify it by reducing the fraction representing the function. This changes the domain, but it does not change the limit at any number because it changes the domain only by possibly adding this finite number of values to the domain, and we know that that doesn't affect the limit. If for the reduced fraction the denominator doesn't have value 0, then limit equals the value of the reduced fraction. So if f of x is g of x over h of x in reduced form, the f of x equals g of c over h of c. What if the denominator is 0? Turns out that if the denominator is 0 but the numerator is not, then for rational functions, one-sided limits will exist but will be infinite. We will come back to this when we talk about finding one-sided limits. So that leaves the case where both the numerator and denominator are 0, and it follows from something called the factor theorem in algebra that the rational function can always be simplified. X minus c will be a factor of both the numerator and the denominator. And you can either try to factor, or if it's too hard to factor, you can always divide by x minus c, both the numerator and denominator. Examples we'll be doing will be at first quadratic or cubic, and you can always factor either by using the rule for the process of factoring quadratics or by using factoring by grouping and other techniques from high school algebra. So let's do a simple example now. So we're finding limit as x approaches 2 of a certain rational function. It's a good idea to always start by evaluating the function at that number where we're trying to find the limit, because it's possible that the denominator is not 0 and you won't have to do any more work. Now the denominator for this function is x cubed minus 3x squared plus 2x. If I plug in 2 for x, I get 0. Well, what about the numerator? That is also 0. So that tells me that I should be able to factor and reduce. So let's start by factoring the numerator. It has 4 terms, so I will factor by grouping. The first pair of terms, x cubed minus 3x squared, has x squared as a factor in common. So I can pull that out of the first pair, have x squared times x minus 3. The next 2 terms, minus 4x plus 12, has 3 as a factor in common. But I want to have x minus 3 as other factors, so I should also factor out the negative. So altogether I should factor out negative 4. 12 is negative 4 times negative 3. So negative 4x plus 12 factors as negative 4 times x minus 3. So now I can factor out x minus 3 from the 2 groups, and that gives me x squared minus 4 times x minus 3. X squared minus 4 is x squared minus 2 squared, so it factors as x minus 2 times x plus 2. In the denominator, x cubed minus 3x squared plus 2x, x is a factor common to all 3 terms. If I factor that out, the other factor will be x squared minus 3x plus 2. You can factor it the way you usually factor quadratics. You should get x minus 1 times x minus 2. So now I see that my original fraction is x minus 2 times x plus 2 times x minus 3 over the quantity x times x minus 1 times x minus 2. The x minus 2's can be cancelled, reducing the fraction to just x plus 2 times x minus 3 over x times x minus 1. The denominator is not 0 when x is 2, so the limit exists. It should also be the limit of the original function, because all we did was change the domain by including 2 in the domain. But the two functions agree except at 2, so they must have the same limit at 2. But since the reduced fraction is defined when x is 2, and it's a rational function, the limit equals the value. So I just plug in 2 for x, which gives me the limit. Of course, we can do this arithmetic. So I get 4 times negative 1 over 2. So the limit is negative 2. This is essentially how we find limits of polynomials and rational functions. Next time we will go and look at, we are going to look at the ways of finding limits of functions or expressions which occur in calculating derivative, which is what we are going to do eventually. I'll stop here for now.